different examples are given in the literature. Even those maps basically are discontinuous at the basically fixed point, but idea of the proof is almost similar. Means we construct the basically this sequence of the iterates, and after that due to the completeness, first we may show this is a basically Cauchy sequence, and due to the basically completeness of the space we prove that, and using that particular type of the condition, this type of the condition, of course that is not a contraction condition, but in the case of the contraction due to the continuity, that limit becomes the basically fixed point. But here this so suppose if I consider Cannon map, this is less than equals to alpha times this is d of x comma t x plus d of y t y. Of course, here alpha is less than half, and of course this is greater than equals to 0 or maybe positive, because when you take this constant constant is 0, then map becomes basically constant map, then by default it has a basically fixed point. So better to take the basically positive, otherwise for 0 it's a trivial thing. So anyway, so this is called the basically Cannon map. So using this basically condition, we can basically prove that limit of the Cauchy sequence is also a fixed point and uniqueness from the same one. And then later on we have the basically Chatterjee map, and then other Jemfer-School. So what did basically Jemfer-School? So in Chatterjee, this they basically just change these distances. So just he consider in place of x dx just x dy and plus d of y tx. And of course, this map satisfying this type of the condition need not be continuous. So that is why this is very important class. This is very important class, because for the continuous map means contraction, particular we can do all the things with the Banach contraction principle. So this is a basically Chatterjee, but of course spelling is little bit different, Chatterjee. So of course next day we have a speaker from Bengal, B.S. Chaudhary will be here by tomorrow evening. Then last time he was here, so then I asked, why what is this pronunciation Chatterjee? Then he said, no, this is Chatterjee, because I asked in the Bengal you have a Mukherjee, Chatterjee and something more, Banerjee, like that, but why this is Chatterjee? Then he said, no, this is a Chatterjee. And then why? Because what is the spelling of T? T-E-A, but what do you spell? T, not Tia. So this was his logic. But of course this is a logic, because this is a Tia and T. So Chatterjee, this is exactly actually Chatterjee. Anyway, so then Jemfer-School, one guy from Romania, basically combined these maps. So this is basically first contraction Tx ty d of xy. Of course here for 0 I always assume basically this is a trivial thing. Anyway, so this is basically, so here we have continuous, but these are need not be continuous. We have the basically counter example in the literature. So then Jemfer-School basically extended this class, and he said a map is said to be Jemfer-School operator if it is satisfy one of them. So either this or this. So Jemfer-School map means it may be continuous, means maybe it's a basically contraction, maybe Cannon map, maybe Chatterjee map. But for the approximate means idea of the proof in the all results is similar. Means construction of the sequence means this Picard sequence, and prove that it's a basically Cauchy sequence, and due to the basically completeness. What happened? Power तो आ रही है? Power तो है? हाँ, it's okay. ये तो बंद नहीं हो गया? प्रोजेक्टर भी बंद होगा? पावर है? पावर तो है, तो बंद कैसे हुआ? ये तो नहीं हुआ कोई ब्रेक हुआ हो, बट लाइट तो ठीक थी. हाँ ओके, चलने लगा ना, अब चलो, रेड हो गया ना, अब ब्लू करो, ऑन इससे करो ना.
इससे ही होगा
है ये किससे हो गया क्या है
ऑफ है।
सर ऑन इससे होता है
रेड
वाले
वाले
से।
हाँ तो दबा के रखो तो
सर थोड़ा टाइम लेता है अगर वो लाइट चली जाती है।
बट लाइट तो गई नहीं थी शायद क्यों
ये
या तो
फ्लक्चुएट हुआ तो लाइट
फ्लक्चुएटिव हुआ ना ओहो
सर 1 मिनट रुकिए हो जाएगा।
बट वो भी तो स्टार्ट होना चाहिए
हो गया।
हाँ ओके नहीं वो तो आ जाएगा शायद वो बंद नहीं हुआ वो तो चल रहा है सब कुछ उसको वो चल रहा है शायद सिस्टम
नहीं सर
है
इसका ऑन कहाँ से होता है ये? अब ऑन हो गया।
शोएब ये कहाँ है ये
अब ऑन कीजिए बंद हो
कर दिया
नहीं वो तो कर दिया आ रहा होगा
लाइट तो नहीं आ रही।
नहीं नहीं अब नहीं अब स्टार्ट करो लाइट बंद होगा हाँ दोबारा करो हाँ अब होगा ठीक है जल्दी नीचे लाइट नीचे अब वो नीचे है लाइट बंद
वो दिखा
हाँ पहले बंद हो गई चल
फ्लक्चुएट वो डीप कर दो
क्योंकि आपको पता नहीं है ना यहाँ का सिस्टम तो इसलिए कहमत काजमी को बोलो
ऑन तो किया है इसमें नहीं आ रहा
उसको बुला के लाओ नहीं नहीं तुम बुलाओ उसको पागल आदमी है
वो तो हो गया ये तो ऑन भी किया नीचे।
नहीं अब आने दो पहले उसको क्योंकि वो बंदा जो करता रहता है उसको ये बहुत ही मक्कार है ये बार बार भाग जाएगा उसको ऊपर ही कर दो थोड़ा खोल के इसको, या कोई हिल रहा है पावर सप्लाई में। ओके पूरा यहीं बैठे रहो, कहीं जाना नहीं बाहर जाइए। ओके so so we have these classes contraction and Kannan and then Chatterjee, and then we have basically Jemfersky operator, and later on wherein they extended this idea to the weak contraction or almost contraction that unify all the things. But every time idea of the proof was almost similar or same, or we can say all these operator contraction and Kannan, Chatterjee, Jemfersky and weak contraction, they were all are the basically strongly Picard operator. So strongly Picard operator means when we have a basically unique fixed point of a map, then this sequence always converges to the fixed point. In the first lecture or first tutorial, Aftab basically defined this term Picard operator, or you can say strongly Picard. So this is a basically one class means, or you can say all operators are here strongly Picard operator, means they always converge to the basically fixed point whenever we have the fixed point set has non-empty, and of course singleton means unique fixed point. But as we know that this another class of the map, non-expansive map, is more important and is a bigger class. So that is why we are interested to find out the fixed point of those operators, and of course for that we have the well known theorems, Kirk theorem, Broder theorem, and other theorem with under suitable conditions. Question is that how we approximate the basically fixed point of those operator. So if we consider this sequence Picard sequence, this is xn plus 1 equals to t of xn, or maybe I can say t to the power xn plus 1 x naught, if we start with any x naught from this. So of course in case of the contraction this always converges to the fixed point, but if I take the basically bigger class that is for example non-expansive map, then this sequence need not converge to the fixed point even operator has a fixed point. So if we take a simple example like rotation map, as we know that of course on the disk not circle. So of course in the rotation map, and this rotation is a basically isometry, as yesterday Professor Khamsi already, so it's a basically non-expansive map, no problem. So if I take basically rotation, and if I take the basically just any point, so T is basically my rotation map or simply rotation, it's a basically isometry and non-expansive, and if I start and if I take simply theta equals to pi by 2, if I rotating by pi by 2, so and if I start from here, so this is basically my x naught, then T x naught will be here by the pi by 2 angle. So this is basically my x1, and then again next state will be here, and this is basically x2, this is T of x1, and next one will be here. So this is a, you can say x3, this is T of x2, and after that we have this one. So this is a non-expansive map, and we start basically just from any point, and if we rotate by the angle pi by 2, then we have only these 4 points. So this is just go and sorry this one and this, and again it will continue. So this sequence never converges to the basically fixed point of this rotation map, even this origin is the basically fixed point. So this is a question then how we can approximate the basically fixed point of the non-expansive map. This was the idea. So people basically came with the basically different idea. So this Kruskolsky, before this Kruskolsky basically he just what he consider, he defined the basically sequence just the average of these 2 points, means element and its image. So basically he defined, so this is basically initially in the Picard this was basically my x1, but now x1 is a basically midpoint of this, that is just or you can say, so this is average operator. So here just we define simply this, so my x1 is equals to just x naught plus T of x naught by. So, it point. So, and now this is basically my x1, and now I will operate t on this part. So, from here I am here, and then now again if I rotate by the pi by 2, so angle this, and this becomes basically more just distance will be this one, and this go more closer, and after that it will closer, and after this it will basically converge to the fixed point, because in every step, because x2 will be here, this is the midpoint of this part. So, it will be more closer, and then it will be more closer. So, in every step next point will be basically more closer due to the midpoint of this. So, this was the idea. So, in general, and of course, on R also we can consider the plot of map. Suppose if I have T x equals to I think minus x, it also works. So, 0 is the basically fixed point on interval, maybe we can consider 0 to 1, or maybe simply or minus 1 to 1. So, if we consider any x naught different from 0, then of course, this sequence never converge, because this is a oscillatory, or you can say divergent sequence. Different, because this is a Picard sequence for arbitrary element, but here if we consider any non-zero, so this will be plus minus plus minus plus minus. So, that is why this is not converge. So, these are the two nice example. So, what is here basically? So, here basically we consider, so this was the idea here, basically Mann came with this idea, and basically just he defined this scheme to approximate the basically fixed point of the non-expansive map. But before that they basically consider, so if I see like this, half of this x naught and plus, idea was from here. So, this is some kind of the convex combination of these. So, if we replace this half as a lambda, then we have basically this conspicuous iteration, because if we take lambda equals to half, then we have that average operator, you can say mid value. So, this is a part of research. So, initially it was only true for the basically half, but if we consider convex combination of this one, of course, means there is some, so lambda plus 1 minus lambda equals to 1. So, this is the idea. But Mann came with the basically more different idea, means or more general form. He replaced this constant lambda by a basically sequence, and sequence in between these intervals. So, this is basically more general this case. So, again so of course, by this scheme, this was given in 1952, that was published in American Math Society. But again we have the basically more large classes of the operator, like pseudo contractive operator, you people know about those, and other pseudo monotone operator, other thing. So, and of course, here for the even for Mann, if I have a basically this sequence x n equals to this is x n plus 1 equals to just lambda n x n plus 1 minus lambda n t of x n. For the discontinuous operator, this fail again, of course. But okay, this Picard sequence also work for the discontinuous operator, no problem for the Cannon and this one, that because these are the basically Picard operators. But again a problem for the basically discontinuous map and more general class. So, that is why people came with the basically different fixed point algorithm, so they can approximate the fixed point of the those operators. So, this scheme Ishikawa was basically given by, of course, Ishikawa, and he defined this scheme in the two steps. And just he defined first yn, just using these two element x n its image, and using this yn. So, this is a basically one point on the basically line segment x n t x n, some point, not extreme point, because my sequence in the basically open interval 0 1, and now choose this that point yn from that line segment, and now you can define x n plus 1. So, this point is fixed here, and this is a basically t of yn. So, this gives the basically another important result in this direction. And in the literature we have the basically lot of fixed point iteration. If time permits, I will discuss some more iterations in the second lecture, because here I am discussing the things in the geodesic spaces. Okay. If we see basically here, whenever we are going to define the iterations in the, of course, these are the basically schemes in the nonlinear spaces, because we have the basically convex combination, we are adding the basically vector, we are multiplying by a scalar. So, of course, these schemes are in the Banach space, or you can say simply normed spaces, because in the normed space we can do these activities. Okay. So, in the literature we have lot of you can say results, very important results, and they have lot of application in the different directions in mathematics and outside the mathematics. So, these fixed point algorithms, they are very useful in the convex optimization problem and differential inclusions, fractals, discontinuous differential equations, optimal control, computing homology of maps, and designing, and so many things, and even in the economics. And of course, this fixed point theorem also has basically very important linkage with the common fixed point problem. So, common fixed point problem, we know that if we have basically two operator on a space, yesterday Professor Imdad also is something about common fixed. So, a point from x is said to be the common fixed point if t of x equals to s of x equals to x. Means whenever we have a system of two linear, so we are always interested in the common solution. Otherwise, for a single equation, how many solutions? Infinite many solutions are there. So, this basically gives the idea just to solve the basically common solution of system of equations. So, this is pointed out by the Takahashi, and these basically approximating the common fixed point also has the basically direct link with the minimization problems. So, as I you see here, we have this is a basically one step scheme, sometimes we call it a one step iteration, and this is a two step iteration, and after that we have some more iteration 3 or like that one, that is a difference. But in 2011 Abbas et al define a basically one step iteration scheme for the two multi-valued non-expansive map, not for the basically single valued, for the multi-valued maps, which is basically more simpler computing than the classical schemes of Mann and Ishikawa. Okay. So, but another observation is here, as I said, we have the Picard, we have the Mann, we have Ishikawa, then we have some more iterations. So, once we define a basically new iteration, so there are the basically two purposes, or you can say we face the two difficulties. One, okay, we have a one iteration scheme, and if we consider a more general class of the operator, whether we are able to approximate the fixed point of that operator by the given. If not, then of course, we go for new iterative schemes. So, this is the one motivation. Another, because once we have the basically more iterative scheme or algorithm, so rate of convergence of the iterative scheme is also very important for the computation point of view. So, it is not always okay, this is my iterative scheme, but motivation was not that, means we have a new map and we cannot find out a approximation of the fixed point of that operator, just I am defining. So, this is not, at least that should have better rate of convergence also. Suppose you have a scheme, but it take the basically 6 hours like that one, then there is no need to define such kind of. So, rate of convergence is also very important if you are not going to define that scheme for a new class of the operator. So, first one, if you are going to define a fixed point approximation this scheme for a new class of the operator, this is a one good thing, but if you are basically define a new fixed point algorithm for the existing class, then rate of convergence should be better than the previous one. Otherwise, we can approximate the basically solution by the previous schemes, then there is no need to define the basically new scheme. So, so this is another important importance of the to define a new iterative scheme, means define a new iterative scheme with higher rate of convergence or better rate of convergence. So, that is why Abbas basically give basically this scheme just for the two multi-valued maps, and of course, for the common fixed point, because here we have the, and he approximate the basically, means authors approximate the common fixed point of the multi-valued map. Okay, and so this is basically one line, means one direction, you can say. So, then later on these guy from Iran, Abkar and Islamian, and people from Thailand, they basically extend this scheme for the finite and countable family of the map on uniformly convex Banach spaces. Okay. So, as I mentioned here, this was the basically for multi-valued map. So, we will recall some basic tool from theory of the multi-valued maps. But before going to this, so as I said, to define the such kind of the fixed point iteration, we need a basically this convexity structure. So, in the Banach spaces, these kind of the these schemes are well defined, but if we think outside of the Banach spaces or linear domains, means that is in the non-linear domain. For example, in general metric spaces. So, question is that how we can define these schemes, because on the metric spaces we do not have the basically linear structure, means we cannot on abstract spaces we cannot add the elements, we cannot multiply by a scalar. And of course, this is very important, because always means our task is always either we go for the bigger class of the map or for the bigger spaces. Of course, Banach space are very important, they have nice geometry, but as a mathematics point of view and something else, these non-linear domains are also very important. For example, means this was a question, why Banach theorem is very famous? Why? Because available on the basically abstract set, means metric setting. So, that is why you can apply in maximum cases. Otherwise, all are the basically, for example, Kirk theorem and broader, because all Banach space are not like uniformly convex or reflexive blah blah and this normal structure property. But Banach fixed point theorem, you have an entire space, only you have a contraction, then it has a unique fixed point. So, even this is basically true or hold on the basically entire space. On the same side, Kirk theorem and this broader, they are on the particular domain. If we have a closed bounded convex subset of a uniformly convex or maybe reflexive with normal structure, then non-expansive map has a fixed point. So, this is the beauty of this theorem. So, same thing is there, if we want to study basically these fixed point algorithms in non-linear domain, then how we can do, because in metric setting we cannot define these schemes, because we need a basically some kind of the convexity, or means linear structure, means addition and scalar multiplication. Okay. So, so there is a basically some spaces, that is a basically again a basically class of the metric space, subclass of the metric spaces, that is called the geodesic spaces. So, at least we can extend these things for the one particular class of the geodesic spaces, and in the recent year some well known fixed point theorem from Banach space, or you can say from linear domain to the extended to the these geodesic spaces, or you can say in particular cat 0 space, another name is complete Hadamard spaces. Because there we have a some means idea of the convexity, this is not exactly similar to that one, but similar things are there, that is geodesic segments are there. So, I am going to basically define. So, as I said, to study these kind of the results in the nonlinear domain and fixed point algorithm, in the nonlinear domain we need a basically convexity. So, of course, initially these type of iteration defined in the Hilbert ball, and these are the particular Hadamard manifold. So, these are the some important like Brouwer fixed point theorem and Sauder fixed point theorem, they basically extended to these geodesic spaces or space in particular cat 0 spaces. So, I am going to these detail. Okay, before going to define a basically cat 0 space, this is a well known distance function between the two closed and bounded subset, that is called the Hausdorff-Pompey metric on this class of the metric space closed and bounded subset of K. So, we can measure the basically Hausdorff distance between the two sets by this formula, maximum of the supremum of, and of course, here this is basically infimum distance is here. So, infimum of, first we take the basically infimum, and then after that we take the basically supremum, and overall we will take the maximum distance. So, this is a basically your Hausdorff distance. This is a very important distance to study the basically fixed point result. and this is a basically multi-valued version of non-expansive map. So, for the single valued it was like d of t x t y, but in case of the multi-valued these become the basically sets. So, that is why in place of d we can write basically h, because my map is a basically multi-valued map and where h is a basically Hausdorff distance. So, if my alpha is less than of course 1, then this is called the multi-valued contraction, and for this one Nadler extend the Banach theorem for the multi-valued map. Nadler in 1969 extend Banach theorem for the multi-valued map, and of course in that theorem has lot of application in the fractal geometry and fractals. But if we take alpha equals to 1, then this becomes the basically multi-valued non-expansive map. So, its definition is here. So, this is a Hausdorff distance between these two sets T x and T y. So, these are not two element, now these are the basically two sets, closed and bounded set of K. So, this is a basically a multi-valued non-expansive map, and idea of the fixed point for the multi-valued map is x belongs to its image set. So, for the single valued map of course, you know T x equals to x, but for the multi-valued map T x of course x belongs to this set. So, and it belongs to the basically set. So, that is why in the case of the Nadler fixed point theorem there is a means fixed point is not unique. Fixed point is not unique because this element can be belongs to the several sets. So, in the Banach it was a like it has a existence part, fixed point was unique, but in the case of the Nadler fixed point theorem fixed point is not unique. But of course, we can do iteration and like those things. Okay. And this is very important lemma, very useful to prove the basically Nadler fixed point theorem. If we have the two closed and bounded subset of x, and for each a in A and for any epsilon we can find out or there exists of course for the this class B such that distance between the two element, these two element A and B is less than Hausdorff distance between capital A and capital B plus epsilon. Otherwise, without epsilon it may be different, because this is not a natural distance. Of course, this is a metric, and this is basically also metric, and if my x is a basically a complete metric space, then of course this CBK with this Hausdorff metric is also a complete metric space. So, if I basically remove this epsilon part, then of course this inequality may be reversed, means distance between the 2 point can be greater than by the distance Hausdorff distance between the two sides. Of course, if we consider the diametral distance supremum distance, then this is always less than, but in the case of the Hausdorff distance, distance between the 2 point can be greater than by Hausdorff distance between the two sides. So, that is why this epsilon is very important, otherwise inequality may be reverted. We can find out lot of points. Okay, this is a one very nice geometric property from the Banach space. I do not remember because maybe Professor Amin discussed this property in the Banach spaces for the fixed point. This is very important property. Once we have the approximate fixed point sequence, then using this property we can have the existence of the fixed point. So, what is this property? A Banach space is said to satisfy OPL condition if we have a sequence which is converges weakly to x, then this implies that lim sup of norm of x n minus x is strictly less than lim sup of norm of y x n minus y for distinct x and y. So, this is very important property to prove the basically fixed point of non-expansive mapping especially, and these are the basically some spaces they enjoy this property. So, these means all Hilbert spaces, and even here all LP spaces p greater than 1, they basically enjoy this OPL property. But on the same side, when p is different from p, capital LP fails to satisfy OPL condition. So, just we can have this. So, because I recall this property because I will use this property in this setting cat 0 spaces. Okay. So, now I come to the basically this is a little bit different thing, cat 0 spaces. So, what are the basically cat 0 spaces? So, cat 0 space is nothing at, they are the basically geodesic spaces, means if we have the basically 2 point, then we can join by some geodesic. So, first of all we have a basically metric space with metric D, and then we define a geodesic path between the basically joining two points of x and y is a map. So, geodesic, what is geodesic? It is a basically continuous map between the 2 points. So, of course, this is a C is a basically my map from a closed interval 0 r, of course, which is subset of r to x, such that value of C at 0 is at this point, initial point this x, and value of the C at this point r is y, and distance between these two points is same as the distance between S and T for all S and T in this closed interval 0 1. So, this is called the basically geodesic map simply, and it is a continuous map. So, and now graph of this one is called the basically geodesic path between these 2 points. In particular, of course, from here we can see easily distance between these two spaces, because these are the points in the space, because x is my anymetric space and these are the point from the real line. So, this map C is a basically isometry, because d of x y equals to r total B, because at this is, if we put here 0 and here r. So, this is basically at 0 is x and at r is y. So, that is why d of x y equals to simply total length is 0 to r is r. So, that is why it is a basically isometry. Okay. So, here this is a little bit means geometric visualization. So, this is basically my space, and these are the basically my 2 point x and y. So, for that we have a basically this continuous map from 0 to L, or of course, in the previous I took the basically 0 to C, same thing. So, if we have the basically other 2 point T and T prime, then corresponding point on this geodesic is like C of T and C of T prime. So, for this map or this path, this is a basically image, or you can say graph of this, and this is called the basically geodesic. So, image of geodesic path under C is called the geodesic segment between x and y, which is basically denoted by this bracket, square bracket x comma y, whenever such a segment exists unique, because this is not necessary that it is unique geodesic, because we are not in the equilibrium plane or like that one. So, once it is basically unique, then it is basically denoted by this symbol just. So, this is a basically geodesic segment just joining these 2 point x and y. Okay. So, now from here now we are going to just have an idea of the just any point. So, any point z from this geodesic, and of course, this is a part of the basically my metric space. So, just this any point z on this geodesic can be represented by z equals to 1 minus alpha x o plus alpha y. So, this is a just notation, this is not a basically plus sign, because we are working in the metric setting. But yeah, this is a notation similar to the basically line segment. If we take the basically in the non-linear space, if we take any point on the line segment, that point can be written as a linear combination of the convex combination of that one. So, this is just now notation similar to that one. If we have a line segment, if we take any point, that point can be written as the convex combination of these two extreme point. But there we have a basically plus, we have a addition in the normed space, we have a scalar multiplication, but here we do not have anything, but we have the basically just representation. This is not basically scalar multiplication here, and this is not addition, just this is a representation similar to that one. So, but what is the meaning here? It means that if we have any point on this geodesic, suppose z is here, then we can calculate the distance of z from x, and we can calculate the distance of z from y. So, what is the meaning here? If this z is basically on the basically my geodesic segment, then distance between x and z will be alpha times d of x z, and here now we can do, because this is a real number, this is a real number, so that is why we can multiply, no problem at all. And distance between z and y is equals to 1 minus alpha d of x y. So, this is the meaning. So, z is a such point is satisfying these two conditions, or any point satisfying these two conditions, then that can be represented by this symbol. Okay. So, because this is a we generally people took this notation due to the same in the non-linear spaces, otherwise it is a basically different meaning. Okay. So, now using these geodesic segment, then we can define geodesic spaces. So, a metric space is called geodesic space if any 2 points on x are joined by a geodesic for every any point. and x is said to uniquely geodesic if there is exactly one geodesic joining x and y. Okay. So, generally a metric space is said to be geodesic if every pair of the element can be joined by a uniquely geodesic. So, now here we can define the basically convexity in this sense. So, a subset C of x is called convex if C contains every geodesic segment joining any 2 point in C. Definition is similar as in the basically linear case. What is the convex set? Any line segment containing the point contained totally inside same. So, here is basically we do not have a basically line segment, we have a geodesic segment. So, that geodesic segment should be inside the set. So, if my basically geodesic is exactly line segment, so in the case of the linear space this geodesic becomes exactly line segment, this is the idea. So, definition is exactly same. So, for any 2 point geodesic segment joining any 2 point should be inside C. So, such a space is called the basically convex set in this sense. Okay. Now, using the basically these geodesics we can define a geodesic triangle. So, of course, triangle means it has the basically 3 vertices. So, it is denoted by delta of x 1 x 2 x 3. So, these point can be, so because this is a basically part of the metric space. So, here it can be joined by a basically geodesic because we are in the geodesic spaces. So, my triangle may be like this, maybe in R2 it is exactly Euclidean triangle, but corresponding to the this one. So, a geodesic triangle means it is a basically a triangle which can be joined by the basically different geodesics. Okay. So, comparison triangle for the this geodesic triangle is a basically triangle in the R2 plane, E2 means R2 Euclidean plane. What is the it is denoted by delta bar, and this delta bar is a basically geodesic comparison triangle for this geodesic triangle in the Euclidean plane R2 or E2 such that distance between the basically these points xi bar, xj bar, these are the basically corresponding point is same as the distance between the basically corresponding. So, distance between the x1 bar x2 bar is same as the distance, but here distance is the Euclidean distance and here the basically distance we measure by the metric d, whatever the metric here, but it should be basically same. Then such basically triangle is called the basically comparison triangle in the R2 Euclidean plane, and these points are called the basically comparison point. If we take any point on the this geodesic segment, then of course we have the another point on the suppose I have a basically point here x, then corresponding point I have a basically x bar here, then distance between this point and this one is of course by a geodesic by a d, it should be same as the distance between the xn bar and x bar in the comparison triangle. So, such point is called the basically comparison point to this. Okay. So, delta B basically geodesic triangle in X in metric space or geodesic spaces, and delta bar is a comparison triangle in R2 Euclidean plane R2, then delta is said to satisfy the cat 0 inequality. So, basically cat 0 inequality, cat is basically name of the 3 famous mathematician, C for Cartan, very famous geometers early Cartan, and these are basically another 2 Russian mathematician Alexandrov something and Toponov. So, basically they people study these spaces in detail long back. So, in 70s or like that, one guy basically honor of them, he put the basically name, it is basically cat 0 space. Here 0 means there basically these geodesics has the basically curvature, non positive curve means curvature 0 or less than 0. Otherwise, in general we can define cat k spaces means of means these are the basically curve, geodesics are basically curve, their curvature may be anything. So, if I say curvature k means cat k space means it is a collection of the all those geodesics whose curvature is k or less than k, but for simplicity we are just taking the basically curvature 0 or less than means non positive curvature curves. So, anyway, whenever we have a basically just these geodesic here, and here we have a basically comparison triangle, and if we take the basically 2 points on the basically 2 geodesic, then we have corresponding comparison points is here. So, what is the basically possibility here? Distance between x and y and distance between x bar and y bar of course may be equal, may be less than or may be greater than, But of course, for our study or maybe definition, if for all points distance between x and y, because this is basically a geodesic triangle in the metric space. So, that is why distance given by the metric d is less than equals to distance between the comparison triangle comparison points on a comparison triangle in Euclidean space. So, if all the basically geodesic triangle, if all x y from this geodesic triangle satisfying this inequality, then we say that delta is said to satisfy the cat 0 inequality. Because idea is here, maybe my geodesic may be like this one also. Suppose if I have a basically surface, maybe concave type and convex type. So, if I take the basically just this type of the because geodesic may be like this one also, like this, but distance may be in that case greater than the basically distance between the x bar and y bar. So, we have the basically convex surface and concave surface. So, if we draw the basically on the concave outside, geodesic will be like this one, otherwise inside. But for our basically study, as we said for commutativity, yesterday Imdad said that to, and of course Professor Khan is also there, idea of the weak commutativity. So, commutativity means okay, this is a very hard condition. So, I think Sesa came with or James sir, weak commutativity. So, of course, this distance between the T S x and S T x maybe or maybe just it is maybe equals to something like d of what is not for commutativity like this one S x and T y. So, it means these distance equal to, but for our fixed point theory problem he considers this is less than equals to, because contraction is basically like this type, because otherwise it will becomes a basically expansion. Maybe this may be equal or maybe greater than, but we say it is a weakly commuting if we have the less than sign. So, same thing is here, maybe distance is greater than, but we want to basically solve the problem. So, that is why we just take this part less than equals to part, means we consider only those geodesic triangles they satisfy this type of the distances. Of course, other side is there, no problem. So, this is a basically geodesic triangle satisfying this inequality, that is called the cat 0 space. So, this is basically my final definition. A geodesic metric space is called cat 0 space exactly if all geodesic triangles satisfying this comparison inequality or cat 0 inequality. Complement is there, but we are not interested in the complement, that is a different story. So, so now these are the basically some example, some of the examples are well known, but some are basically little bit not standard, or maybe you can say. So, this is basically from the geometry. So, complete and simply connected Riemannian manifold having non-positive sectional curvature, these are the example of cat 0 space. All pre-Hilbert spaces are the basically example of and arteries and Euclidean buildings. There is a book, so maybe we can go through these. These are the little bit more technical terms, but these are the well known examples are here, and complex Hilbert ball with hyperbolic metric. So, this is an important thing. So, what is the basically, it means that this is a part of the metric space, because all metric space do not satisfy this means this kind of the thing. So, what is the connection between these spaces, and we say that all Hilbert space or pre-Hilbert spaces are the basically example of the cat 0 space. So, this is basically my metric space, and you say this is basically my Hilbert space, and this is basically my Banach space. Of course, we have this non-empty intersection in between this, and this is a basically well known established result. This intersection part is basically cat 0 space. No, sorry. Hilbert space. So, because this is also a subclass of metric space, Banach space, this is also a basically subclass of the metric. So, these are the basically my cat 0 space. So, intersection of these two class are exactly basically Hilbert space. So, that is why all Hilbert spaces are the cat 0 spaces. So, this is a very nice observation. So, anyway, what is the basically, if you recall basically last 3 days lectures, either we have the results in the metric setting in general over the domain, especially for the contraction class, and after that we have the basically results. Starting result for the non-expansive mapping was in the Hilbert setting. First result by the Broder was in the basically, but later on they proved that result from here to here, means from Hilbert space to Banach space. Okay. So that is why Kirk theorem and Broder theorem and all the things and so on. Now we have lot of results in this part. Lot of people basically extend lot of results from the Hilbert space to the basically Banach spaces or some particular class of the Banach space, like uniformly convex Banach space or reflexive Banach space, but it is a class. So question is that how we can extend basically result from here to here or maybe here to, because this is basically my non-linear part, non-linear domain, this one. Up to it is linear, this common part is here, but this part is basically remaining part. So question is that how we can extend the basically Brouwer theorem, because where was the Brouwer theorem? Brouwer theorem was the basically finite dimensional Banach space. So theorem was here. So question is that how we can study that theorem in this part. So this is a very important generalization from linear domain to non-linear domain. So of course, as I said, Brouwer theorem already extended to the cat 0 space in the some maybe 15 years back, like that, and later on then Sauter theorem is also extended to here, and other important theorem is already extended to these non-linear domains, because in this theorem we need a basically convexity. If you remember, if we have a continuous map which is defined on a closed convex ball, or you can say compact and convex. So every time we need a basically convexity, either even for the existence part, not for the approximation, because in all basically theorem, either it is a Broder theorem or maybe Kirk theorem or Brouwer theorem, Sauter theorem, Tagnov theorem, always we need a convexity. So that is why we cannot do these things here, but after this idea of the geodesic convexity, people are able to do similar things in the non-linear domains. So this is a very important generalization of, these are the very important spaces where we can extend. Even people are not doing the fixed point theory only. Here we have the idea of the duals also. So in this part, people are also working in the function analysis part, they are also defining the duals also. Means they are doing the basically lot of operator theory in this part as well. Means operator theory involving the basically some concept from the convexity, or you can say a result involving the convexity for the operators, they are basically extending or studying those results from Hilbert or Banach to cat 0 part. So this is not exactly fixed point theory, people are doing in the other domains also to these spaces. So that is why these spaces are very important. Okay. So so already I just pointed out any point in the this geodesic segment is denoted by this one, and meaning is just distance between this t times or lambda times this, and then for any x y z in x and t in closed interval 0 1 we have this inequality. So in place of the line segment, now we have a geodesic segment. So distance between the set, this is some kind of a set because geodesic is a set. So distance between the line segment, but here is a geodesic segment, and this point z is basically less than equals to 1 minus t times distance between x z plus t times distance of y z, and this lemma is available in the non-linear space, and proof is very trivial, but this is also true for the non-linear domain, particularly for the cat 0 spaces. So this is a important lemma. Now actually so in the previous year me and my colleague Izaruddin, we basically work in this direction, and then basically we extend this lemma, because this lemma was basically for the 3 arbitrary points. So we extend this lemma for the arbitrary endpoints. So if we in a cat 0 space, if we have v1 v2, these are the endpoints, and we have scalars, means their sum is 1, then we have this inequality. So we extend, so here O plus means lambda I vi means this one. So this is basically not is a exact convex geodesic convex combination is here, and if we consider this one, then this becomes exactly convex combination of endpoints in the linear spaces. So, this lemma is basically also true, it is basically exactly similar previous one. So, it is a generalization of this lemma. Okay. Now, this is again a very nice stuff. In this morning Professor Amin discussed these things in linear domains in the Banach spaces. So, this is another important, because he was asking one question when he defined basically this part. So, we can go through the orbit, another is basically go through the approximating sequence. So, here, but we are in the metric setting in the non-linear domain. So, we will go. So, that is why we need that approach in this cat 0 spaces here. So, definition means in looking, okay, we are a metric space, so we cannot write x n minus x, but reason is not that, okay, that is a different thing, but reason was that. So, here we work with the basically that orbit. So, a definition exactly similar for a bounded sequence in a complete and complete cat 0 space means same thing, means every Cauchy sequence has convergence, because overall we have a metric there. So, that is why definition of the convergence and Cauchy is same thing. So, so he already defined in the morning this function, first of all R x x n for a bounded sequence and for a given x, then asymptotic radius is noted by small r, but this is different from this r, notation same people generally use, and of course, this is basically started in the cat 0 spaces by the Kirk itself. So, this is the infimum of these functions, and then he defined the basically asymptotic center. So, it is a collection of those points from the x for which these two functions coincide. So, it is exactly same definition, but in the setting of metric set. So, first of all people do basically did in the metric setting, and of course, once it is basically in the metric setting. So, that is why this is also true here, no problem at all. So, we will do the basically same thing. So, now this is a very nice result. In the cat 0 setting, this asymptotic center always has basically singleton, always non-empty, and it has a basically single, and that singleton becomes the basically fixed point. So, this is always whatever your map, this is a basically, this is always consists exactly one point, and this is proof is available in the literature. So, of course, I will share the slide, so you can go through the proof. So, this is the beauty of this result, because we always interested in the basically asymptotic center. First of all, it should be basically non-empty, and if it is a basically singleton, and then that becomes the basically fixed point. But in the cat 0 space, this setting, this is a basically already this is exactly one point. Okay. So, now we are here. So, overall we have a basically strong convergence with respect to metric D. And now in the Banach space, of course, we have the basically, or this part we have another idea of the convergence, that is the weak convergence. So, question is that can we have a similar analog of weak convergence in this part as well? Yes, answer is yes. So, this is a basically another notion of the basically convergence, that is known as the delta convergence. In delta means that triangle, geodesic triangle here. So, what is the basically this one? So, a sequence x n in x means cat 0 space x is delta convergent to x if the unique asymptotic center of u n for every subsequence u n of x. So, x kya ho? X is the unique asymptotic center for every subsequence of this one. Then we say that this sequence is delta convergent. So, this is a basically similar thing in this part, and we write delta limit of x n equals to x, and this is called this. So, this is a basically analog of the basically weak convergence from Banach space, this part to the cat 0 space, and one is already strong convergence is here. So, if you go through the basically these fixed point iteration or convergence analysis of the fixed point iteration, you have the two types of the analysis. One is the basically strong convergence. It is basically available for the Picard operator, because all the basically those Picard operator always strongly converge. But initially for the non-expansive map we have a weak convergence. Of course, after putting some condition we have the strong convergence, but initially it was a basically weak convergence result. So, so that is why we can have the two types. One is the basically strong, another we can study the basically, if means convergence is not strong, then we can think about the delta convergence. Similar means if there is no convergence, strong convergence, then generally we go for the weak convergence in this part. And this is a same inequality This is also very nice result. If you remember your OPL property, where is your OPL property? This is in Banach space, and by default this is automatically hold in cat 0 spaces. Yes. So, because it is due to the basically uniqueness of the asymptotic center, because asymptotic center is always here unique. So, that is why this distance. So, if we have a sequence and this xn converge delta convergence, not strong convergence to x, and we have different y from x, then uniqueness of the asymptotic center imply this one. And what is this? This is the basically your OPL property. So, by default we have this property in these spaces. So many things are very easy to prove the or approximate the fixed point in this one. So, these spaces are very important. So, okay, these are the some important result which are similar to the basically Banach setting or nonlinear space setting. So, every bounded sequence in complete cat 0 space admit delta convergent subsequence. And if xn is a bounded sequence in closed convex subset of a complete cat 0 space, then asymptotic center of x is in lies in K. Okay, this is another important lemma which is basically very useful in the minimization problem, and this lemma is known again basically for the 2 points. So, if we consider only 2 points, then this is already very useful in the minimization problem, and people use this lemma very frequently, but we extend this lemma for n points in nonlinear domains. So, this is also a work with my colleague Izar that is published in Mediterranean Journal of Mathematics. So, if we have a complete space cat 0 space and we have these n plus 1 points and we have these n scalar, their sum is 1, then so here basically this is a square, previous inequality was different, this was not a square here, this is here. So, this is basically different. So, this inequality is different where. So, this is our, so d of this is a geodesic combination or segment of these n points and then x, then whole square is less than by this sum. If we take only just 2 points, then it is a basically very important problem in the. So, now I come to the basically, so already existence part for the non-expansive map in the cat 0 space is given by the Kirk and Van Naek, these guys started this study in this direction. And again reason is that why Kirk was interested in these space. Initially he was a geometer, he was not analysis. So, that is why he knows these spaces very well. Even when I was a PhD student, I wrote a one paper and I submitted to that paper to computer math application, and paper was on the symmetric spaces, something fixed point theorem on the symmetric space, some kind of the contraction like that one. And Kirk was the basically referee, and he pointed out so many things about that paper and terminology especially. Do not say this is a symmetric spaces, these are the semi-metric spaces, and he defined all the basically these spaces, what the mean by the symmetric space in the geometry and what the mean by the semi-metric space, because he was a basically man. So, now I later on I realized that of course, this is not a man basically from analysis or means a fixed point theory guy, he was a basically from the geometry. So, that is why of course, that paper accepted later on, we did the basically lot of corrections. So, now first so now I just for this talk I just consider the one scheme. So, we have a basically cat 0 space and K be a convex subset of cat 0. So, convex here means by the geodesic segment, not by the line segment. And these TIs are basically my just n map, because I recall a one result by the Thai people and Irani people, they extend that result for finite countability. So, basically we consider for the finite number of map, and of course, these are the multi-valued maps, and we define a basically scheme here like this. So, we define this sequence x n plus 1 by this one. So, this O plus has the basically meaning, and here order is fixed, and where this y I n belongs to the basically image set, because my map is a basically multi-valued map. So, here just we put the basically elements, and this element basically from the this T I x n, such that distance between T I and P is less than Hausdorff distance between these two set plus this epsilon. So, this is a basically we can write this inequality due to the basically lemma by Nadler. I studied it initially, and these are the basically my scalar in this one, their sum is 1, and limit of this eta I n when n tends to infinity is basically 0. So, this is basically my scheme. If I take this scheme in the just non-linear space, then this becomes simply plus sign. Okay. So, for this scheme we have a this lemma first of all, because I am going to just say something about the approximation of the common fixed point of these non-expansive map. So, we have a multi-valued non-extensive map which is defined on a closed convex subset of Hadamard space. Hadamard space means complete cat 0 space, as I already say you Hadamard space known as means complete cat 0 space known as the Hadamard space is also, and their fixed point set is non-empty because by the existence theorem we know they have the basically fixed point. So, that is why. So, this is the same idea. First of all we check the consistency. So, fixed point is there. Now, we go to the approximation of the fixed point, or you can say to find the solution of the problem. But here we have a basically this condition means value of the or action of this multi-valued map on the fixed point is basically singleton set or simply P for all fixed point of these map. Capital F is a set of the fixed point intersection of these one. Okay. So, if I have a this sequence defined by this 3.1 with this condition, then we have these two conclusions. So, what is these conclusion? Limit of the d of x n p for all fixed point exist, and second we have this sequence approximating sequence is also here fixed point means limit of d of t I x n x is 0 for all I. Proof is not difficult. I am not going, just using some calculations we can do basically these proof. First of all we prove this sequence is a basically decreasing sequence of non-negative number which is bounded below. So, that is why it is convergent. So, no problem. So, that is why this one has a basically limit, means this limit is exist. And then second part we prove this sequence, and so I am not going into this part as well. So, proof is there. So, now this is a basically main theorem first of all. So, let K be a non-empty closed convex subset of a Hadamard space, and we have everything same. Then this sequence x n defined by the 3.1 converges to the common fixed point, but which convergence? Delta convergence. So, this sequence delta converges to the common fixed point of these operator T 1 T 2 up to T n, means we can approximate the basically common fixed point of these operator using this scheme in cat 0 space. So, this is a one delta convergence result. Proof I am not going again, just this is a line. Now, we have the another important result in this direction. As I said, we have one is delta convergence is here, but we have overall we have the strong convergence as well, because this is a subclass of the metric space. So, that is why we can also prove the some strong convergence result in this setting. So, everything is same, but if we put this condition limit infimum of the d of x n comma f is 0. So, f is a basically set of fixed point. If we have this condition, then this sequence also strongly converges to the basically common fixed point of the T i's with this condition, and this is basically if and only if condition. If we have a this sequence is strongly convergent to the common fixed point T I, then this limit of the infimum of the d of x and f is 0, and if we assume this, then we have the strong convergence result. And then of course, we have another important strong convergence result just replacing this condition. So, for the single valued map Center and Dodson they define a basically one condition that is known as the condition A, and Khan and Fakhruddin extend these definition for the multi-valued version, which is basically weaker than the compactness of the domain. And even we can prove the basically strong convergence result if we assume the compactness is here. So, this is another basically form of the strong convergence result. So, we have the different set of condition, then we can prove the basically strong convergence. Maybe in the one situation one result is applicable, another situation another result is applicable, we have the compactness, then we can apply that version. If we have this condition, then we can apply the this version of the theorem, and if we have this condition, this is called the condition A, then we can apply this theorem. Still we have the basically strong convergence result. So, what is this theorem? Condition A. So, a family of the map multi-valued maps is said to satisfy the condition A if there exists a non-decreasing function f from r plus to r, f of 0 is 0, then f t is positive for positive real, then d of x comma t I x is greater than or equals to f of d of x comma means distance between this x and fixed point set. So, using this condition we have the again strong convergence result for the same scheme. So, basically we have the basically two strong convergence result and one delta convergence result for the this scheme. As I said in the previous results, I put this condition, this is called the endpoint condition, and of course, this is a little bit difficult or strong condition. So, if we basically just consider the basically different class from the CBS, basically my result here on the this one closed and bounded subset, but if I reduce the basically this class to the this proximal. So, what do I mean by this proximal? So, a subset k of x is called proximal if for each x in x there exists a element, distance between this element and set k is same as the basically distance element means of course distance. So, there exists a element small k in k. So, distance between this small x and small k same as the distance between the small x and whole set k. So, this is called the basically proximal distance. So, if we take see in the basically R 2, then this become the minimum distance, that is perpendicular distance circle or other things if we geometric this. Okay. And if you remember Khamsi also pointed out this result. Okay, if we have the basically non-empty closed convex subset of a uniformly convex Banach space, then this is basically proximal. So, means we have that point. So, that distance between the point, and we can always find out a point which has the basically minimum distance. So, that is why this is very important. So, in uniformly convex Banach space, every closed convex subset is proximal, and we denote this class by the PB k, and then we define the same thing here, and our scheme becomes like this one. So, now there is no need of this one. Reason is that because when we have the proximal distance, then distance between the capital H of, because if you remember basically this scheme previous, this becomes 0. Where is my scheme? This part. So, because that distance becomes basically due to the proximal, because we are considering the closed and bounded and convex subset here. So, that is why we can relax that condition. So, everything is same, sequence is same, only just we drop that condition, because here distance between P and this point is same as the distance between the P and this set, because this is a closed and bounded subset in uniform Banach space. So, that is why this becomes basically exactly equal, and then we have the basically exactly similar results without this endpoint condition. So, of course, we have now we have a smaller class, but we remove that strong condition, that is endpoint condition. So, this is the basically of course, in the research sometimes you are generalizing the other side. So, then of course, you have to reduce the other side of the part. So, same thing is here. Of course, my now class of the operator is smaller, but we remove that condition T P of T of P equals to P, then we have exactly same result. Now, we come to the basically one application of this scheme. Of course, there are lot of applications. So, this is called the image recovery problem, and this problem is already studied in the linear domains in Hilbert spaces and Banach spaces by the Japanese people and other guys from USA, Takahashi group. So, what is the basically just problem? If we have a basically non-empty closed convex subset of a real Hilbert or Banach space such that intersection is non-empty for this finite. Okay. So, problem of image recovery may be stated as original unknown image x, or maybe element, you can say have a basically common element in the intersection, because in the image processing they also use this word, but mathematically we can say we have to find out that common element in this intersection, because intersection is non-empty. So, question is that how to find out that common element. So, so original unknown image x is known a prior to belong to the intersection given only by the metric projections PCJ of x onto Cj. So, using these projection map, metric projection map, we can recover this element x by the iterative schemes. So, for that people use the different iterative schemes, but to study this problem we will use our scheme. So, one of the basically example from the literature is this one. Bregman constructed this sequence using the cyclic projection. So, basically he construct the sequence like this one using this projection, metric projection. So, just he started just any arbitrary element x naught and define x 1, it is a basically image of this projection on C 1 and x 2 x 1 projection on C 2 over this P, and after x m and then x m plus 1, then again repeat the basically projection over C 1. Of course, element is x m, but basically here. So, this is a basically cyclic, and after that we have this sequence, and then he proved that this sequence converges weakly to an element of this intersection part, means we can find out the common element in this intersection if intersection is non-empty in the Banach spaces. Okay. So, this was a one problem, and of course, here we have the basically weak convergence. So, this is from the literature, this as I said the Japanese people Kitahara, Takahashi also died, you people know Takahashi, Tamura, they study basically these type of the problems in uniformly convex Banach space using the convex combination of non-expansive retractions and other things. And recently these guys from Spain, Espinola and Fernandez Leon. So, Espinola is basically also work on this renorming problems from University of Valencia and Xavier. So, this guy, but now almost they are also going to retire. Anyway, so they proved the basically this very nice result in the complete cat 0 space. Let K be a non-empty closed convex subset of complete cat 0 space or head mat, then we have basically these two facts. First of all, these metric projection Pk of x, of course, of this element onto K is a singleton. This set is singleton. Another this operator Pk means this projection is a non-expansive retraction onto K. So, these are the basically two important results we will use. So, just we have this result. Basically, this is an image recovery problem in the nonlinear domains, you can say in the cat 0 setting. So, what is we have exactly a family of the closed and convex subset of a cat 0 space, complete cat 0 space such that intersection is non-empty. Problem is same, how we find out the common element in this intersection, and if we if Pi is a basically metric projection onto Cj, then for any x naught in x we define a basically sequence, it is exactly same. Then this sequence always delta converges to the common element of this intersection, means similar to the weak convergence result due to the Bregman. So, proof is not so difficult. So, idea of the proof is very simple. So, in view of the previous lemma, these operators are the non-expansive retraction onto Cj, and as these are the non-expansive map. So, a fixed point set of P is a Cj, that is why the lighting if we take in place of the means this singleton, and then single valued version of our result means just proximal point last second result we obtain a basically desired result, because when we because this sequence is same as, and if we take this is a single valued version of our result, then that sequence converges to the delta converges to the common element, or we have a basically common fixed point, or we can approximate the common fixed point of these family. So, this is nice. For that just we can see this with a simple example. So, for simplicity we have a one example in higher dimension also, but for simplicity we take here x equals to r with the usual norm. Then we have a basically family of the closed and bounded convex subset Cj 0 1 upon j is non-empty closed and convex subset of x. So, of course, intersection is non-empty. Okay, so define the mapping Tj from x to Cj metric projection by this rule Tj x equals to mod of sin x up over j for all x, and we easily just prove that these are projection map and which are the basically non-expansive map. And using the basically MATLAB program, and if we choose the basically different sequences. So, of course, here we basically just consider the format. So, yes 4 an1 an2 an3 an4, and we have the basically this sequence, and of course, their sum is 0, and if we start the basically with some initial guess, then always we have basically common element, because what is the basically common element of this one is 0, because if we change the basically s, 0 is always common element. So, this sequence always converges to the basically common element 0. Of course, when we have the basically different because it depend on the basically 0 is common element, but from where I am basically taking the point. So, it may be very far, then it will take the basically more steps or iteration. If it is very near, then it take the basically less, but every time this sequence is converged to the basically common element of the this intersection part. This is just graphing, and of course, in the just some previous year we also did, utilize or apply this kind of the iterative scheme, of course, in the linear domain for the OD and PD fractional differential equation, and some people are working in the basically signal processing problems, image deblurring problem, and this is a very nice paper. Sir, this is that paper, I will send you. Okay. So, this is the by Patrick Combat and Poscat fixed point studies in the data sciences. So, this is basically IEEE transactional signal processing. So, in the first maybe 10 pages they just recall the fixed point problem, and then after that they use fixed point algorithm, proximal point algorithm just for the this kind of the problem, especially image deblurring problem and signal processing problem. So, these schemes are very useful basically in the data sciences as well. So, they have very nice book also from the Springer, and basically initially I think one is French, another is this is French, and this is now work in the University of British Columbia. So, this is very important reference, so you can go through this reference. Okay. So, as I said, it has the basically lot of things in the minimization problem. So, idea is there basically just we have to minimize the basically sum of the two operator fx and gx, and so where f is a real valued and proper convex lower semi continuous and g is a real valued and convex differential function. So, some of our students are here from convex optimization area. So, they are very used to this type of the problems, and so what the game here. So, to find out the basically minimizer or minimization of this one, it is same as the to find out the fixed point of the proximity operator of G. So, this is the basically proximity operator. So, fixed point of this operator is same as the basically minimizer of the basically this or minimum value of this operator. So, that is why this problem is very important. As I said, it links with the basically minimization problem as stated by the Takahashi. So, lot of students from our department working in this area in various inequality side. Convex optimization problem. So, this is just idea, means how we connect the basically fixed point to the that problem. So, of course, there is a different literature, for that we need another GYAN program, because it is a very vast area, it is not a, but this is the idea, means how we connect the fixed point to that problem. Anyway, and of course, this operator is a non-expensive operator. So, we can apply our these iterative schemes to the to study those problem in the convex optimization problem side. This is something for the hybrid non-expensive mapping. So I am not going. This is another important thing, just for the future point of view. So, here we define some kind of the convexity, that is a geodesic convexity, but we have basically some other spaces we have different kind of the convex structure. So, we can think these result for these other type of the structure. So, this is the hyperbolic convex metric space. Of course, this is a part of the cat 0 space, but maybe first we think from Banach space to the hyperbolic convex metric space, then we can go to the cat 0 spaces, and life is of course there. After cat 0 we have cat 1 also, that is a little bit more complicated. So, Professor Kimura from Japan is doing some work in the cat 1 spaces. So, these spaces are more important than of course, a cat 0, because here calculations are similar to the Banach setting. Okay. But in cat 0 cat 1 space, life is a little bit different.
Some tools are similar.
Yeah, something, but here almost maximum changes are things. So, but this is basically what it is. So, this is a basically pattern, but convex metric space is also given by the Takahashi in 1970. So, he has some kind of structure, and metrically convex space by the Karl Menger. So, these are the basically abstract form of the convexity. So, we can think about this kind of the problems in these spaces, not iteration, maybe Brouwer theorem, maybe Sauder theorem, maybe Kirk theorem, or maybe like that one. Okay, so there are these some references I use. Okay, thank you very much. So I have another talk on iteration. So in that one we consider the some different iterations and then prove, because there are two important aspects of the fixed point iteration. One is the convergence, another is the stability analysis. That is very important for computation point of view. So in that talk I think I do not have a now chance to deliver that talk, because every talk is already scheduled in the academic calendar, academic program. So stability means that whenever we